So, um, yeah, so we talked about how scientists used to believe that light was a wave, and then we had the results of the photoelectric effect, which wouldn't make sense if light was a wave, because just to review again, if light is a wave of electromagnetic radiation, then the result of the photoelectric effect would have been that any frequency of light that shines on a piece of metal would be enough for the metal to eject an electron. But the results were not that. The results were there was a minimum amount of frequency that was required before an electron would be thrown off. So then you had Max Planck, who was studying hot objects, and he was the one that came up with the idea that maybe heat, which is also energy, is released from objects in little packets or quanta. So then we get to the 1900s with Albert Einstein, and he expanded on Planck's theory by introducing the idea that EM radiation has a dual nature, which is both wave and particle. So he said that light displays many wave-like properties, but it can also be thought of as a stream of particles, which is the analogy that I gave to you last week. If you think of an actual ocean wave, you can look at the wave as a whole, or if you zoom in, the wave is actually made of particles or molecules of water. So these stream of particles in light, he called photons. So a photon is a particle of electromagnetic radiation that has zero mass, but it carries a quantum of energy. Remember that a quantum is an amount of energy. And energy is dependent on frequency. So we go back to that equation, which is the energy of a photon is equal to wavelength times frequency. So we're going to have some more evidence to back up the dual wave particle nature of light. So we look at what's called the line emission spectrum of hydrogen, and I'll explain what that is. So if you remember back to chapter 3, when I talked about the cathode ray experiment, and I said that when you have a gas that's sealed in a glass tube and you electrify that gas, it glowed, right? That's why we got the cathode ray. The same thing happens for any gas. So when a current is passed through a gas at low pressure, so it's exactly the same setup as the cathode ray tube, the potential energy of some of the gas atoms increases, so that electrical energy that you are applying to the gas inside the tube is going to be converted into potential energy. Because remember, one of the principles of one of the principal laws of science is the conservation of energy and the conservation of mass. And these both state that energy and mass are neither created nor are they destroyed. So it basically just changes form. So the lowest energy state of an atom is called its ground state. And when an atom has a higher potential energy than its ground state, we call that an excited state. So these neon signs, I'm sure that you've seen them in your life around town. Basically, those are molded glass tubes that contain different noble gases. And obviously they all plug in. And so when you plug it in, then of course electricity is applied to that gas. And each gas has a characteristic color when you electrify it. And I'll explain when we talk about electrons and things like that. Part of today's lesson will be explaining why they are particular colors. And it all has to do with wavelength and the EM spectrum. So when you apply energy to an atom, you increase the atom's potential energy. So it goes to an excited state. But just like if you think about little kids, when you give little kids lots of sugar and they get like totally crazy and they like run around, that's like an excited electron. but they can't stay at an excited state forever. So of course, it's going to have to lose that energy and go back to the ground state. When excited electrons lose that energy that they gained to become excited, that's when they emit photons. And that's how we tie this all together with light and photons. Okay, so I just explained that. When it returns to its ground state, it gives off energy in the form of EM radiation. And this, another picture of different neon signs. So the different colors are related to the type of gas that's inside of it. And without getting into too much detail, because part of what I'll talk about today is the detail, but each of these atoms have different numbers of electrons in different arrangements. And so when these electrons move to different excited states, they, how to explain this? They can go to different levels of excitement, and depending on how, what level they're going to, they can release photons of different frequencies and therefore different colors. Maybe it'll make more sense as I go through it. So scientists started to test this theory of the dual wave particle nature of light by passing electricity through hydrogen gas at low pressure. And they saw this very characteristic pink glow from the hydrogen. Then they took that pink light and they shined it through a prism. And if you know anything about a prism refracts light, which means it bends the light. And because light is made of different wavelengths, each wavelength of light bends at a different angle. And that's how you get a rainbow, if you didn't know that already. So when you shine a light through a prism, each wavelength, like I said, bends at a different angle. So for example, sunlight is what is called white light. It is made of the entire EM spectrum. If I can go back to, where is it here? If I go back to this slide specifically, let me get my Keynote app up so I can point, play. Where's my pointer? Here we go. Okay, so we're looking at this range here. I'll just highlight it there. So you can see we've got the colors red, orange, yellow, green, blue, indigo, and violet at the end. And then of course you've got ultraviolet, which is above violet, and infrared below red. We're looking at this range of visible light, and you can see that it has different wavelengths and frequencies between red and violet. So each of these wavelengths will be bent or refracted at a different angle. And that's why sunlight, which is made of all of these colors together, when you combine them all, you get white. And that's what white light is made of. So you shine sunlight through a prism, you get the entire rainbow. But that is not true when you shine, where am I here? Nope, that's not it. I'm past that. There we go. Is not true when you pass this pink light from hydrogen through a prism. You don't get the rainbow. So the bands of light that you get, I believe there's 5 of them. I think, I should have a picture. If not, I'll try to find one. Yeah, I do in a little bit. You get a very specific spectrum. I'll just show you here now. So this is the spectrum that you get when you shine the light through, and I'll explain these 3 spectrum that you get. A spectrum just means like a range, right? So this is what you get when you shine white light through a prism. You get a continuous spectrum. This is all of the wavelengths of visible light, because sunlight or white light is made up of all of the wavelengths of visible color. These 2 are hydrogen. Now you've got 2 different spectra. You've got absorption, which is where the wavelengths of light that are emitted from hydrogen when you shine the pink light through a prism, those wavelengths are absorbed. So they appear as black lines, like basically absorbing it from this continuous spectrum. The most common spectrum that we use, though, is called the emission spectrum, where you see just the wavelengths of light that are separated when you electrify hydrogen and it glows with that pink color, you take that pink light and you shine it through a prism, you get these 4 bands of light, these specific 4 wavelengths of light. And you might be thinking, well, what does that have to do with anything? I promise it all ties together.
Hi, in physical science, we're now studying about the different models of the atom. And one of those models was the Bohr's model of the atom. I want to show you the evidence for the Bohr's model of the atom, which is basically the line spectrum produced by different gases, or when different elements are heated up, they produce a light of a very specific color. That was the evidence for the electron jumps between one energy level and another energy level. Of course, to do that, to show it, you have to turn off the light. So I'm going to turn off the light now for a second, and I'm going to show you the difference between what the spectrum looks when we look at the regular light bulb, incandescent light bulb, compared to a light bulb that's filled with one kind of gas. So first it will get dark, and then it will get bright. So here I have a regular incandescent light bulb, pretty strong. I'm going to put the diffraction grating now in front of the camera to show you the continuous spectrum of this of light produced by incandescent light bulb. So here to the side, you can see now the spectrum produced. Basically, the white light is divided by the diffraction grating into the individual colors, and you can see that the spectrum is continuous. We see all of the colors of the rainbow in the spectrum. I'm going to turn off the light bulb and turn on the hydrogen lamp. Okay. So here I have a light bulb filled with hydrogen at low pressure. And you can see it's kind of a pinkish, purplish light. And again, I'm going to put the diffraction grating in front of the camera so that we can see the spectrum. Now, if you look at the spectrum, you can clearly see definite lines of light. So the diffraction grating takes this pinkish light, and it actually shows you what it's composed of. So here are the colors of light produced by hydrogen. You can see the very strong red, and then the 2 different kinds of blue, the light blue and then the kind of navy blue. And then there is a little bit, you can see to the very left, there's a very, very weak line there as well. So that's spectrum produced by hydrogen.
So, oops, hold on. There we go. So here you can see the line emission spectrum. So these are the specific, this one's really faint here on the left-hand side, but these are the very specific wavelengths of light that are emitted when hydrogen atoms go back from their excited state to their ground state. Now, basically, the relevance that this has to atoms, because obviously this is chemistry, so we're talking about it, is that remember, like putting everything together, when you excite electrons, when you add energy to atoms, the electrons become excited. So they go to a higher energy state, but they can't stay there forever. So when they go back down to their ground state, they emit photons. Now, remembering what Planck said about quanta, these little packets of energy, that they contain specific amounts of energy. And then Einstein came along and called them photons and said that photon is related to frequency. And remember that frequency and wavelength are basically 2 sides of the same coin. So basically this is, I'm going to try to write, no, I'm just going to use the laser here. So here's 1, 2, 3, 4. And I can't see on my iPad the same screen. So I'll try, nope, 1, 2, 3, there we go. And 4, you know what, like, you know what I'm trying to label here. So we've got 4 specific frequencies of photons that are emitted from the hydrogen atoms when the electrons go from excited back down to ground state. What that tells us is that there are 4 specific energy levels for the electrons in a hydrogen atom, because if they become excited and they go back to their ground state and they emit a photon, but you're getting 4 different frequencies, which means you're getting 4 different photons with different energies in them. So this was evidence to support the Bohr model of the hydrogen atom, in that electrons can exist in these energy states. And this is the significance of this experiment showing the line emission spectrum. Does that make sense? Should I try to explain that again? I feel like it makes sense in my head, but I'm not sure if it makes sense in your head. So I think let me just continue. It might make some more sense when we look at organization of electrons. So the hydrogen atoms are excited by whatever amount of energy added to them. Scientists expected to see the emission of a continuous range of frequencies, or the continuous spectrum, because remember, we thought that light was a wave. So you should see that continuous spectrum like you saw in the beginning part of the video, like the whole rainbow. So the question is, why are the hydrogen atoms only giving off specific frequencies of light? So attempts to explain this observation led to an entirely new theory of the atom called quantum theory. Okay, so here's where I start to get into the details of explaining those results and how it relates to the arrangement of electrons, which is what this whole chapter is about. So like I said, when an excited hydrogen atom falls back from an excited state to the ground state, or to a lower energy excited state, it emits a photon of radiation. The energy of the photon is equal to the difference in energies between the 2 levels. So if you look at this little graph here, we have, let's say, energy level 2 and energy level 1. If a photon is released from this electron or this atom, same thing, that goes from energy level 2 to energy level 1, the energy of the photon is equal to the difference between these 2 levels. Makes sense, right? So if, for example, I'm just going to make up some numbers. Let's say this is 20 and this is 10. The energy of the photon will be 20 minus 10, which will be 10. That will be the energy of the photon. But what happens if there's more than one level? So if I draw out, if I draw out more than one level, and you have an electron that goes, say, from level 4 to ground state, that is the energy that will be released, the difference between level 4 and level 0. If, however, it falls from level 4 to level 3, it'll emit a photon with less energy, right? So you can see how hopefully you see how the line emission, if I go back here and I go back to, where is it? Here. So these lines that you see in the spectrum are indications of what levels exist in a hydrogen atom. So you've got a red line here. And remember, red is a long wavelength and a low frequency. As you move towards violet, you have a shorter wavelength, but a higher frequency. So these photons being released on this side are of higher energy than this one on the left, or on the right-hand side, sorry. Okay. So changes of energy, which is a transition of an electron from one level or orbit to another, is done in isolated quanta or isolated amounts. Remember, a quantum is a specific amount of energy. Quanta are not divisible. There is a sudden movement from one energy level to another. It's not gradual. It really just jumps from like 4 to 3, 4 to 2, 4 to 1, 4 to 0, whatever it is. There's no in between. It's a lot like when you step up and down a ladder. You can't step in between the steps of the ladder. You're either on the first step or the second step. So electrons work in the same way. So hydrogen atoms, again, looking at just the emission spectrum, because that's what we focus on, it emits only specific frequencies of light. This shows that the energy differences between the atom's energy states are fixed because every single hydrogen sample, whether you are wherever in the world that you are, if you take a sample of hydrogen gas, you electrify it, it glows pink, you pass it through a prism or some kind of diffractor or refractor, you're going to get exactly the same 4 lines. So that means that they are fixed, they are set energy levels. So this tells scientists that the electron of a hydrogen atom, sorry, that's my dog, the electron of a hydrogen atom exists only in very specific energy states. Let me just let him out real quick. Sorry about that. Okay, so the bottom line or the big picture is that you've got hydrogen. When you electrify it, you're exciting the electrons, which means that they're going to start emitting photons of energy. And when you separate that light, which is created by the photons, you get these 4 specific frequencies of light, which shows you that there are 4 specific energy levels that electrons can exist at. So we've gone from the models of the atom that we've had. We had the J.J. Thomson plum pudding model, where you had random positive and negative charges spread throughout the atom. Then you had Rutherford's gold foil experiment, which defined the nucleus as a very dense, small, positively charged center of the atom with electrons around it. The next model we get to, because we are, what do you call it? We are, I don't have the words today. We are defining more, we're better defining the definition of an atom, what it looks like, and the behavior of all the parts, I guess. I know that there's a word for it, but I can't think of it in the moment. Never mind. So Niels Bohr is the next guy to come up with a new model of the atom. He proposed a model of hydrogen that linked the atom's electron with photon emission. According to the Bohr model of the atom, the electron can circle the nucleus only in allowed paths or orbits. Okay, so it's not like you just find electrons randomly flying around the nucleus, but you find them in very specific areas. When the electron is in one of these orbits, the atom has a definite fixed energy. The electron, therefore the hydrogen atom, is in its lowest energy state when it is in the orbit closest to the nucleus. This is a theme that you will see throughout when, the study of chemistry, is that the closer to the nucleus electrons are, the lower the energy is. I'm sorry, he's scratching to get back in. Oh my God. Come on. Sigh. Okay. Hopefully he'll be quiet now. Okay, so the orbit closest to the nucleus represents the lowest energy. The idea is that the further away from the nucleus you get, the higher the energy is of the electrons. And in between these levels or these orbits, electrons cannot exist in these spaces. Just like the rungs of a ladder, the steps of a ladder. You're either on step 1 or step 2 or step 3. You're not in between. And like I said, when electrons move away from the nucleus, when they get excited and they can jump to higher energy levels, they get further away from the nucleus. They have to, although, jump back down because they can't stay excited forever. Okay, I'm going to skip that because I already talked about that. All right, so how do we explain the spectral lines? When in a given orbit, the electron isn't gaining or losing energy, but it can move to a higher energy orbit by gaining the energy equal to the difference. The same way that when a photon is released, the energy of the photon is equal to the difference in the levels. It's the same thing when you are moving an electron to a higher energy level. So let's just go back to our levels again. Let's say this is 5, 10, 20, 30. So if you have an electron at the ground state and you want it to get to level 3, you're going to have to give it 20 energy. I'm just making up numbers, so I'm not putting a unit to it. If you give the electron 15 energy, it can only go up to level 2. It can't reach level 3. Okay. So also when the electron goes from level 3 back down to the ground state, the photon that it releases is going to have an energy of 20, equal to the difference. When the hydrogen is excited, the electron is in the higher energy orbit. And when it falls down to a lower energy level, the photon is emitted in a process called emission. All right, this diagram might make it a little bit easier to understand because we've got the levels here. So to move from one level to the next, you have to supply the atom, therefore the electron, with enough energy for it to actually reach the higher orbit. If you don't, it's going to stay where it is. So n equals 1 right here, that's the lowest energy. This is the ground state. If you move up to level 2, you have to have enough energy to get you to level 2. And level 3, same way. So here we've got the greater distance from the nucleus going out to n equals 4. And if you go from 3 to 2, you're going to release a photon that's equal to the difference in energy levels between these two. Okay, explained that already. Has equal to energy to difference. Yep. All right, so based on the different wavelengths of the hydrogen spectrum, relaying it back to those specific lines that I talked about, Bohr calculated that those are the allowed energy levels for the hydrogen atom. He then related possible energy level changes to the lines in the spectrum. And we've got 3. Oh, I wrote this down somewhere because I couldn't remember which one's which. Where is it? Here we go. So we've got 3 spectrum series here. We've got Lyman, Balmer, and Paschen. So I looked it up because I couldn't remember. The Lyman series represents the wavelengths in the ultraviolet range. The Balmer series represents the lines in the visible range, and the Paschen series represents the wavelengths / frequencies of light that are emitted in the infrared range. So the Balmer series is the only one that we can see. The Lyman and Paschen series we can't see without special instruments to be able to see UV and IR light. Bohr's model explained the spectral lines so well that many scientists thought it could be applied to all atoms. But it did not explain the spectra of atoms with more than one electron. It turns out that each element has its own characteristic spectrum. And this is one of the ways that we actually identify what stars are made of, by the way, which I'll teach you next semester. Okay. So